part of our video. I wanted to make a few points about dilations and stretches and compressions, and then we can start graphing. I would like to use GeoGebra again to do this, and you can take notes on this page. I've already copy and pasted a lot of the diagrams for you. So if we want to take a look at what a dilation is, well, essentially a dilation is basically a scaling factor that we talked about in our first unit on similar figures. So here I have a square, and I'm dilating the square against this central point D prime. That is the center of my dilation. So as you can see, as I change my dilation factor, the whole entire square is getting bigger and smaller with reference to the central point, which now looks like it's called E. What happens when I move E? Well, if I move E over to the left and I start dilating, it's still going to do the same thing, but it's going to just dilate the different distances. So it's the distance from, for example, E to D prime here and E to B prime here. So a dilation changes the whole figure both vertically and horizontally by a scaling factor. So I want to distinguish that on purpose from what we call a stretch and compression. So in this example, I'm showing you a sine wave. And we are gonna be looking at sine waves actually in this course, even though it's not necessarily part of grade 10. I just want to show you the difference between dilating and what we call a vertical stretch compression, horizontal stretch and compression. So if I were to dilate this sine wave, what I'm going to see is movement in both the x and y direction. Okay, as we saw earlier, it's going to pick a point, and I can actually move this point if I wanted to. Maybe I can't. And, well, I could, just not right now, I've fixed it, but the whole entire graph compresses and stretches based on a dilation. A vertical stretch and compression, as you can imagine, just does an operation vertically. So what you'll notice when I actually stretch this, when I use the slider to stretch this, all my x-intercepts stay the same. So you can see that there's no horizontal movement here, but it's getting vertically taller and skinnier and or shorter and what looks to be fatter. And as you can imagine, if I use my horizontal stretch and compression slider, I'm going to get the same thing, but it's horizontally. Okay, so as you can imagine, based on our reflections from last time, all my y values here stay the same. It's my x values that move. Okay, my x values that are translating. Conversely, all my y values are changing here. So my x values stay the same, but my y values are the things that are changing. So if you want to take some notes on that, that would be great, but I have copy and pasted the diagrams there for you. And what I just want to reiterate based on last time is vertical stretches actually do change the shape of a figure, whereas we talked previously about translations and reflections maintaining the shape of a figure. Well, vertical stretches and compressions will do it. And notice that I don't say horizontal because we are not doing horizontal things until grade 11. So something to look forward to. Yay. And I want to put it all together and talk about the parameters a, h, and k of our parent function. In order to do that, I first want to go back to GeoGebra and I want to show you how our parabola changes as a function of a, h, and k. So we've already looked actually at h and k. We know that h moves our parabola left and right based on whether it's positive or negative. We know that our v value, our k value moves it vertically. We've seen this last time. So let's actually stop these and bring them both back to 0, and let's talk for a minute about how a changes our function. So if we connect this to what we were just doing with reflections, we'll notice actually that as our A value changes, it has a relationship with two things. It has a relationship between reflections and the parabola, and also the stretch or compression of our parabola. So as A gets bigger, my parabola gets skinnier. Now for a brief period between 0 and 1, so let's move this slowly actually. When A gets back to 1, we have our parent function again, but as A gets smaller than 1, our parabola gets bigger, fatter, until we get to 0. And at 0, actually, this is meaningless. We don't have a parabola because we're multiplying our function by 0. What happens when A is less than 0? Well, as you can imagine, it's reflected. So a negative A value represents a reflection in the graph of a parabola. Now this is technically fatter than the parent parabola, so A equals -1 is the size of the parent function, it's just flipped. And then as we go more and more negative, it'll get skinnier in the flipped down direction. So as you can imagine, if we move around all three of these are different kinds of parabolas that we would see and we would need to be able to graph. So without further ado, let's get to that. So let's just make a quick summary of the parameters of A, H, and K, and we'll start with the easier ones first. So if I look at K, which we call our vertical translation, up or down. Okay, if I consider K equals 0 in the middle, when K is greater than 1, when K is greater than 0, we know we're going up. When K is less than 0, we know we're going down. So it separates really nicely into these two different regions. Similarly with H, and we call H our horizontal translation, left or right. Okay, when H equals 0, we have no movement. When H is greater than 1, 0, we're going right. When H is less than 0, we're going left. And we just said to remember to keep in mind that H is separate from this negative sign. Okay, so for example, if I gave you y equals 2x minus 4 squared, H is 4, for example. Okay, so now let's get into the A value, which actually requires quite a bit of analysis. So what I'm going to do is actually divide this into a few regions. So when A is 0, this is actually meaningless. Okay, and that's because, as we saw in that simulation, it just becomes a flat line. But then we also have to worry about when A is -1 and when A is 1. So I wanted to separate our number line, our A number line, into these regions. Okay, so now that we have our number lines separated into these four regions, the first thing I want to talk about is what happens when A is negative. So when A is negative, okay, we know that in this case, okay, there is a vertical reflection. Okay, meaning that it's facing down. And one way we can remember this is with a sad face. So when anytime A is less than 0, the parabola is facing down. Anytime A is greater than 0, however, we have no reflection. So we just can write no vertical reflection. Okay, and we can remember this with a happy face. When A is greater than 0, when A is positive, our direction of opening is up, facing up. Okay, so now we have to think about these regions here. Now that we've talked about reflections of parabolas and I've cleaned up my diagram a little bit, I want to talk more about vertical stretches and compressions. So let's start with the easiest case, and that's when A equals 1. When A equals 1, the shape is exactly that of our parent function, y equals x squared. If I were to reflect this vertically, meaning if A was -1, it would have exactly the same shape as my parent function. It would just be facing downward. So this would have the shape y equals -x squared. And of course, you would still have to apply the vertical and horizontal translation, but this is the shape. Remember, we said that this is meaningless, so we don't have a diagram when A is 0. But now I want to talk about what happens with these other regions. So as we noticed, when A is greater than 1, our graph gets tall and skinny. When A is less than 1, our graph is facing down and it's still tall and skinny. When -1 is less than A, but A is less than 0, the thing is facing down, but it's wide and fat. When 0 is less than A, but A is less than 1, it is facing upwards and also fat. So basically, you have a visual image of what your graph should look like given these different parameters. Now, let's just summarize them down here by naming them. So let's remember that we have y equals a, x minus h squared plus k. And I will do the vertical parameters in red. So our vertical parameters are these two. We have A, and A is responsible for a vertical reflection if it's negative. It's also responsible for a vertical stretch or compression. The other vertical parameter is K, and this one is our vertical translation, up or down. Okay, and finally, our H value is our horizontal translation, left, or right. And again, just to try to hit the point home, that's H. We ignore the negative sign. Just a couple of notes. So translations and reflections. So translations are slides the position but do not change the shape, whereas vertical stretches and compressions change the shape of a figure. Okay, so here's another big fact. Because of this, when transforming a graph, order matters.